Hey guys, this is Mr. Peterson. I'm just going to do a short video on exponential growth, and really it's more of a video on manipulating exponential and logarithmic expressions and equations and using properties of logs and exponents. Okay, so let's quickly review what an exponential equation is. So it's something that looks like y is equal to k, or k is some constant, raised to the x power. And the key characteristic here is that the x, or independent variable, is in the exponents. So let's look at an example with some real numbers. Say we have an equation that's 5 raised to the 2x power is equal to 15,625. So again, this is an exponential equation because our independent variable, this x, is inside the exponent. And so to solve this, I need to use logarithms, and I can rewrite this equation as log base 5 of 15,625 is equal to 2x. One way to think about it is I'm taking log base 5 of both sides. That's the inverse function of 5 to some power is the log of base 5. So effectively what I've done here is I've taken log base 5 of both sides, and that will get rid of my exponent. And I've got log base 5 of 15,625 is equal to 2x. And from here it's just a matter of putting it into a calculator. If your calculator doesn't have log base 5, you may have to look up change of base formula. But from here, it's really just a matter of punching in numbers to a calculator. And so when I do that, I get 6 is equal to 2x, so x is equal to 3. Now let's look at another example. Let's say we have e to the 1.4x power is equal to 76. Alright, so e is Euler's number, which is a number that shows up in math. It's kind of like pi in that it's an irrational number. It can't be written as a fraction, and it's approximated as 2.71828. You could list digits past the decimal forever, just like you can with pi. It's a really interesting number. There's a lot of really cool applications for it, and it shows up a lot in exponential growth. And so we would solve this equation the same way. I would take the log base e of both sides, and we have a special symbol for a log base e. We call that the natural log, and we write it as lowercase ln. I think that's derived from the Latin name for it. But when you see that, that's a natural log, which means a log base e. So if I take the natural log of both sides, that exponent goes away, and I just get 1.4x is equal to the natural log of 76, and I can plug that into a calculator. Your calculator should have a natural log button, and when I do that, I get x is equal to 3.093. Now let's apply this to the example of lily pads in a pond. This is something that was illustrated in one of the other videos posted with this assignment. And so remember, we start out with 1 lily pad, and the next day we have 2, and then 4, and then 8, and every day they're doubling. I'm not going to draw all of them here, but you have 16, 32, 64, and that pattern continues. And so this here shows one of the properties of exponential growth, is that it's a constant time to double something. So in this case, it's just a day. Every day, the number of lily pads is going to double. And now by writing all of this out, I've basically made a table here where I have my independent variable is days and my dependent variable is the number of lily pads. And so I can come up with an equation that describes this data. It's going to look something like y is equal to 2 to the x minus 1 power. And you can check that by just plugging in numbers. If I plug in 1 day, 2 to the 0 power is just 1, so I get 1. I plug in 2 days, I get 2 lily pads. If I plug in 3 days, I'll get 4, and that you can check that yourself and make sure that that pattern holds true for every day. And then more generically, I can write this as y is equal to n times 2 to the x minus 1 power, where n is the number of lily pads that I'm starting with, so the number on day 1. In this case, it's just 1, so it doesn't really do anything. But if I wanted to model something where I'm starting with 4 lily pads or 8 lily pads, then I can just use this equation and plug that in for n. This is a perfectly valid equation. I can plug in days for x and get lily pads out for y, but I want to convert this into an exponential using Euler's number, just to practice our properties of exponents and logs. So the first thing I'm going to do is take the natural log of both sides, and then I can use my properties of logs to split the right hand side of the equation into the natural log of n plus the natural log of 2 to the x minus 1 power. Remember, if I have multiplication inside of a logarithmic function, I can always split that up and rewrite it as the sum of 2 logarithmic functions. I can also move the x minus 1 exponent. Remember, if I have an exponent inside of a log function, I can always rewrite that as multiplied outside of the log function. So natural log of 2 to the x minus 1 can be rewritten as x minus 1 times the natural log of 2. And then, to get rid of my natural logs, I'm going to take the exponential of both sides. So I'm making both sides the exponents to Euler's number. On the left-hand side, e to the natural log, those cancel. I'm just left with y. And on the right-hand side, I can write this as e to the natural log of n times e to the natural log of 2 times x minus 1. So remember, when I multiply exponents with the same base, I add the exponents. So we kind of did that in reverse here. And then e to the natural log of n is just n, and the natural log of 2 is, we can approximate as 0.6931. You just put that in a calculator. And so my final equation, y, number of lily pads, is equal to n times e to the 0.6931 times x minus 1 power, where x is the number of days. And so we can use this equation to model the lily pad growth for a pond where lily pads double every day.